Solving polynomial inequalities. In this first example, we want to solve 8x minus 27 is less than 2x cubed minus 3x squared by graphing. Well, these are going to work a lot like quadratic inequalities, where we do want everything on one side and a 0 on the other side. So I'm going to go ahead and subtract the 18x and add the 27 to the other side. So I'm solving 0 is less than 2x cubed minus 3x squared minus 18x plus 27. And that was just to keep a positive leading term here, positive leading coefficient. But if we want the 0 to be on the other side, then what we'd have to do is think about it as 2x cubed minus 3x squared minus 18x plus 27. When is that greater than 0? Right, so we want the inequality, the shark mouth to be eating the 2x cubed part. So we have to flip it if we want it to be on the left-hand side. Alright, so in order to graph it, we need to have it factored. So 2x cubed minus 3x squared minus 18x plus 27, how do we factor that? Well, it has 4 terms, so we want to factor by grouping. So we're going to create our 2 groups, and we're going to factor out an x squared. So we're left with 2x minus 3. And then here we'll factor out a negative 9, and we are left with 2x minus 3. And so we have the same factor in each term that we're going to pull out. So we have 2x minus 3 times what's left over from the first term is x squared minus 9 is left over from the second term. So review of factoring by grouping. But x squared minus 9 is the difference of squares, so we have to factor completely. So we have 2x minus 3 times x plus 3 times x minus 3. Alright, so now that it's fully factored, we know how to graph it from our previous steps above. So what we want to do is ultimately find the end behavior, the zeros of the function, and that's really all we need. We don't need the y-intercept. We really just need the x-intercepts and the end behavior for the general form. So here I'm going to go ahead and kind of do this in a different way, or slightly different notation in my work, because this is all just scratch work for me. So I know that my 0 here is going to be 3 over 2 with a multiplicity of 1. And then I'm going to have it's a 1, negative 3 again with a multiplicity of 1, and then a positive 3 again with a multiplicity of 1. So I have 3 over 2, and it's going to cut. I'm going to have negative 3, and it's going to cut, and I'm going to have positive 3, and it's going to cut. And then my leading term, well, let's not work with the factored version. Let's just go ahead and look back at the standard form of the polynomial, 2x cubed. So the end behavior is that the right side points up and the left side points down, like regular x cubed. That's positive. So again, we're not concerned with the y-intercept. We don't have to really care about it, although it is pretty easy to find because we have standard form. So if I let all these x's be 0, the y-intercept is 27. So it's like way up here. Let's fake it and say this is 27 up here as the y-intercept. So here we're going to pick up where we left off. We'll cut. We'll come up here. We'll cut, and connect. Right? So we're going to cut through all 3 x-intercepts and then match our end behavior. So what we are looking for is, where is this polynomial greater than 0? So if I do this by graphing, the way that I want to think about it is, where am I above the x-axis, right? Greater than 0 is above the x-axis. So if we kind of highlight those regions, I'm above the x-axis between these 2 x-intercepts, negative 3 and 3 over 2, and I'm above the x-axis beyond this x-intercept of 3. So that's why we really need the x-intercepts. That's where we can possibly change from above to below the x-axis. So let's describe these intervals that would be from -3 to 3 over 2, open, when I'm greater than, not greater than or equal to, and +3 to infinity. In this example, we'll solve quantity x minus 3 times quantity x plus 4 squared times quantity 1 minus x greater than or equal to 0 algebraically by creating a sign chart. So algebraically means by creating a sign chart as opposed to doing a graph. Well, thankfully this is already in factored form. So what we need to do is set this equal to 0. So again, similar to quadratics, what we need is the zeros, but since it's already factored, x minus 3, x plus 4 squared, 1 minus x equals 0, we can easily find all of the zeros. We get x equals 3, x equals -4, and here we'd get x equals 1. So what's the value that will make 1 minus x equal 0? Well, +1. So these are my zeros. So in the same way you'd find them to graph them, we're going to find them, but to put them on a number line. So we're going to go ahead and graph our number line. And the domain of any polynomial is all real numbers. So our number line will have -infinity to infinity. And we'll plot our zeros. -4 is a 0. We have +1 is a 0. And +3 is a 0. And then we go ahead and we are interested in, again, what's happening over each interval. So what's happening sign-wise, like is it positive or negative, when I'm between -infinity and -4, or between -4 and 1. So instead of testing every single value, we can pick a test point value, right? So up here, I usually put my test points. So -5 is to the left of -4. Between -4 and +1, we have 0. Between 1 and 3, we can pick the nice whole number 2, and after 3, we can pick 4. And we plug these test points into the factored version of the function because we want to know what is the sign of this entire function. We want to know whether this entire function is greater than 0, whether it's positive. So we want the sign of x minus 3, x plus 4 squared, and 1 minus x. So we're going to have to plug each of these test points into the x's here. But let's try to make our lives a little bit easier and think about each of these factors for a second. So in particular, the one in the middle. So the factor in the middle, x plus 4 squared, it doesn't matter what I plug into it. It will always give me a positive number because I'm squaring it. So I really don't have to worry about plugging these test points into the middle term. It's just going to be a positive and that's not going to affect anything. So I just have to plug the test points into the outer two factors, x minus 3 and 1 minus x. So -5 minus 3, that's a negative. Again, the middle term is always positive. So we can either ignore it or just always put a plus there. And then 1 minus -5, that's going to give me 1 plus 5, or 6, so that's another positive. So altogether, I have a negative interval. So I don't want that interval. I want, when is this whole thing positive? Greater than 0 means positive. So this first interval is negative. I don't want that one. Let's plug in 0. 0 minus 3, that's negative. Again, the middle part's always positive, don't have to think about that, and 1 minus 0 is positive. So again, I have a negative interval overall, which I don't want. So now we substitute in 2, so we get 2 minus 3, that's a negative. I said the middle is always positive, but now 1 minus 2, that's a -1. So altogether, I have a positive. So I have two negatives, they're going to cancel and give me a positive. So I do want this interval here between 1 and 3. Now I want to know when I'm greater than or equal to 0, right? So positive or equal to 0. So I want to include 1 and 3. So I'm going to have x is in the interval 1 to 3 with closed brackets around 1 and 3. And then let's check 4. So if I substitute in 4 minus 3, that's going to give me a positive. And then the middle is always positive, and 1 minus 4 is going to give me a negative. So overall, this interval is negative. So I do not want this last interval either. Now, there's one small thing that we have to make sure that we don't forget now, though. We wanted to know, when was I both positive or equal to 0? So in this interval from 1 to 3, I captured my zeros of 1 and 3 with these brackets. But this negative 4 value, that's also a place where the function equals 0. So I have to include this one value, negative 4. So what I'm going to do is I'm going to make space for it and say it's negative 4. I'm going to list that one value in curly braces, and all of these values between 1 and 3, including 3. So that's kind of why I do also try to put a z above each 0 to just remind myself, oh yeah, there were more zeros. So as much as I'm canceling out these intervals in between, I still have to remember this 0 over here of negative 4. Now in this example, we're just asked to solve 4x cubed plus 4x squared minus 25x minus 25 is greater than 0. So we can use any method. So here, no matter what, we are going to have to find where this function equals 0, whether to put those zeros on a number line or on the x-axis to graph it. So we do need a factored form. And because we have 4 terms, we're going to go ahead and apply factor by grouping. So we can factor out a 4x squared, and we're left with x plus 1. We can factor out a negative 25, and we're left with x plus 1. We'll pull out the common factor, which is x plus 1. And we have a 4x squared left from the first term, and a minus 25 left from the second term. And now, the quadratic is a difference of squares again. So 4x squared, that's 2x quantity squared, and then minus 5 squared. So we have x plus 1 times 2x minus 5 times 2x plus 5. When is that greater than 0? So we can either graph this now, so find the x-intercepts and graph it, or find the zeros and do a number line. So I would personally say, you know, they're probably equal, but I'm going to go ahead and just go with the number line because that's what most students struggle with at first, is the number line. So I'm going to go ahead and find all my zeros, which would be negative 1, positive 5 over 2, so adding the 5, dividing by 2, and then negative 5 over 2, subtracting the 5 and dividing by 2. So these are all of my zeros. I'm going to put them on a number line that goes from negative infinity to infinity, the domain. We'll plot negative 5 over 2 because that's negative 2.5, then negative 1, then positive 5 over 2. We will pick some test point values, so negative 2.5, to the left of that is negative 3. Oh, and then I forgot, these are zeros. Don't want to forget that. And we have negative 2.5 and negative 1, so in between that is negative 2. And then between a negative and a positive we have 0. And then greater than 2.5 we have 3. So we are plugging these test points into the function. So where is this function greater than 0? So that is positive, right? But again, the best thing to do is to use the factored version to substitute into. So we want to know the sign of the factored version. So x plus 1, 2x minus 5, 2x plus 5. Now there's no factor that we can eliminate here because none of these are squared. So we're just going to have to plug in these numbers into each factor. So negative 3 minus, negative 3 plus 1, we have a negative. Here we'd have negative 6 minus 5, so negative, and then negative 6 plus 5, so still negative. So overall, this is a negative times a negative, so a positive, but times a negative would give me a negative. When I plug in negative 2, we're going to get negative 2 plus 1, so that's a negative. Negative 2 times 2, that's negative 4 minus 5, negative. And then we'd have negative 2, so negative 4 plus 5, that is positive. So the two negatives cancel, give me a positive, times a positive, that's a positive overall. 0 is nice to plug in, because I'm going to get 0 plus 1, that's positive. 0 minus 5 is negative, 0 plus 5 is positive. So multiplying all this, I'd have a negative overall. And then when I substitute in 3, 3 plus 1 is positive. 2 times 3, 6 minus 5 is positive. And 2 times 3, 6 plus 5 is positive. So overall positive. All right, so let's go ahead and before we write up our answer, I mean, this isn't not too bad. We're just thinking about small arithmetic here to think about these signs. But if there's any shortcuts that we can use, I mean, it would benefit us. So one of the things I want to kind of tie this to is the concept of the multiplicity. So each of these factors had a multiplicity of 1. So even though we're not graphing it, we're doing it with a sign chart, we can take the concept of multiplicity and think about what that means. It means that we're going to cut through the x-axis. So let's say if I did a tiny graph real quick, and this is negative 5 over 2, well, we were negative, we were below the x-axis, and if we have to cut through the x-axis, we're going to switch from negative below the x-axis to positive above the x-axis. So if the 0 comes from an odd multiplicity, that means my graph will have to cross the x-axis or cut through it and change sign. So we can see how they bounce between negative, positive, because every single factor had a multiplicity of 1. So at every 0, I'm going to have to change sign. So once I figured out the first one, sign of the interval was negative, I know I'm going to have to alternate. And that only works because the factors are odd multiplicity. Because if we have a factor that's even multiplicity, so now I'm just making something up. Let's say I have 2 and I know I bounce off the x-axis. Well, if I bounce off the x-axis, then the signs don't change. I'm negative and I stay negative. I'm below the x-axis and I stay below the x-axis. So those are just some of the shortcuts we can apply to when we use a sign chart. Now let's go ahead and finish this up. Now I wanted positive only intervals, so I want, whoops, circle this. I want everything but the first and third intervals. So in interval notation, I want everything from negative 5 over 2 to negative 1. And everything from positive 5 over 2 to infinity. And I'm using open parentheses because I want to know where my positive, not where my equal to these zeros. And that is my answer. Whoop.